Hello, and welcome to our continuation of our somewhat more technical webinar series. This one's on the cellular wireless LAN, and today's topic is security. With the new 802.11ax standard, also known as Wi-Fi 6 for us laymen, and WPA3, the webinar is intended for our current customers, prospective customers, business partners, valued business partners, anybody internally that's on the line. Everyone's welcome. We love to have you. My name's Deanne Corcoran, and I work on the Network Business Enablement team, and I'm your webinar host for today. Couple housekeeping items. Of course, the call is being recorded. If you have any objections, you can disconnect. All lines are muted during the presentation. After the presentation, we take questions from the attendees. You may post a written question at any time during the webinar via the questions tab in the webinar panel, and those questions will be addressed first during the Q&A period at the end. The presentation today is being shared live for those of you who have connected online. You can also download a copy of the presentation from the handout section in the control panel. After the webinar today, you'll get a follow-up email from GoToWebinar that will have the recording embedded within it, the email, so you can rewatch it as many times as you'd like. And if you miss getting the handout, you're welcome to reply to the email. It comes to me and I'm happy to send it to you. So again, the topic for today's call is a continuation of our stellar wireless LAN and specifically security. Our speaker today is Jorge Arrasanz, who is a solution architect here at Alcatel-Lucent Enterprise. Go ahead, Jorge.
Thank you very much. It's always a pleasure to be introduced by you, Diane. Thank you so much. Thank you to the audience for being with us today. And as Diane said, we are continuing with this set of technical webinars where we try to introduce more in detail what we can do with our solutions. In this case, with the Stellar solutions, WLAN, and the OmniVista and UPAN in the last session. So today we're going to talk about a little bit about security. Let's go to the agenda and let me highlight my pointer. Okay, now here we are. Okay, this is the agenda that we will follow. We will have a quick overview of what is 11AX today and what is the status of WPA3. Then we will go to some review for some cryptologic terms, and we will see, because we will need it in order to understand later on a little bit why WPA3 has some benefits on it. And last we will be covering more security details or aspects about the Stellar WPA3 implementation, especially using the OmniVista management tool. And then we will finish with other security aspects that are equally important sometimes as the encryption and so on that we'll be covering today. So let's move forward and let's start with the content. Okay, as this is a follow-up, as we said, a set of presentations where I will recall some aspects of the last webinar that was related to how to configure in Stellar and UPAM our identity solution, how to configure AIP with radios, with their own radios or an Stellar radios. And at that time, we started saying the same thing I'm going to say here, which is that security is a process. Security is not a product. Security is not a feature. Security is a combination of many things. But the more important thing that is to follow the process and to adopt the process. So in telecommunications, as we were talking again, the previous webinar, we have some security services that allow us to communicate safely, to communicate with security. These security services are authentication, confidentiality. Confidentiality today is one of the topics where we're covering, is the mechanisms that we have to adopt in order to guarantee that our message that we are exchanging between ourselves is secret, is not captured or cannot be seen by a third party that is eavesdropping in the media. We have integrity as well, which is another part that we are covering today. Integrity is basically the the mechanism, again, is a mechanism that allows us to guarantee that the information I'm going to send you is not modified somehow in the middle. So if I'm going to say you hello world, you should receive hello world and not bye world or whatever. So we have to guarantee that the message in the in this traveling from my side to your side has not been modified in the middle. Then we have non-repudiation. Remember, non-repudiation is the ability to warranty that I already sent you this to you today or yesterday or whenever. And remember the example of the traffic fine when you go driving your car and you go faster than the speed limit and you may get a fine, and then the government probably will send you a fine and you will not be able to say, no, I was not received this fine, I will not receive this communication. No, it has been time stamping, it has been granted that this document has been sent to you, and probably most likely that you open the document. Then we have time stamping, from my point of view, is a security service as well. And then we have access control for accessing the resource. In this case, we are talking always about accessing the network, which is our resource, the resource that we place and put in place. So last webinar, as I mentioned again, we were covering radios AAP 1X, and that was related basically with authentication and access control. So two of these security services. And today we have been covering two other security services, as I mentioned, which are confidentiality and integrity. Because today we are going to talk about how to exchange information with guarantees to be safe. And this is important in every aspect of our today's telecommunications, connecting to the bank or sending the pictures of your children, or sending your medical information or whatever you want to do. Any information you exchange, you should try to keep it safe. You should try to do this exchange with security. But it is key, and it is, or even I would say, dramatically key to do it in WLAN, because WLAN, or most of the radio solutions, are shared medium. So it doesn't care it is 5G or is 4G or is WLAN, the 802.11 protocols, or it is 802.16 one wide area network radio protocols. It doesn't matter. At the end, all the radio is a shared media, and you will find someone that is trying to capture your information. So we need some encryption and we need some hash, because this is the techniques we are going to use to deliver the security service. So confidentiality as a security service is implemented in the real world by encryption, and integrity is deployed, so it's taken to reality by means of hashing algorithms, of hash algorithms that we will see a little bit later. So now, what is the real status of 11AX and WPA3? So as you know, there are two different entities who are backing these standards. The 11AX is backed by IEEE, and while WPA3 is backed by the Wi-Fi Alliance. So complete different animals at different environments, and they work completely different and have different purposes. So if we go to the IEEE 202.11 working group, we can see all the projects. I have already extracted the one that is important for us today, which is 11AX. And as you can see here in the picture, it is scheduled or estimated that the final draft will be closed, so will be really standard body by November 2020. But it doesn't mean that the Wi-Fi Alliance, on the other hand, is already doing the certification process, because at the end the demand for new solutions on the WLAN side is there. So we have to address the market with guarantees. At the end, the Wi-Fi Alliance is trying to guarantee that any certified product is able to interop with any other certified product. So that brings value to the end customers and bring value to the users. So this is the key point. And why is the Wi-Fi Alliance certifying now something that is going to be in 3 or 4 months? Well, basically because we don't expect dramatic modifications that we change everything. So we are probably finishing some specific points that have to be taken, but will not be, as I tell you, modifying in deep any point. Regarding the WPA3, WPA3 was released in September 2018, or in, I don't know, September, maybe, well, in 2018. And if you remember, a little bit later, there was some shock on the media because there was a new security standard, WPA3, and some researchers found some vulnerabilities in the Dragon Blood report, which is the name of this report. The Dragon Blood recommendations are a new set of modifications that the Wi-Fi Alliance introduced in the WPA3 recommendation to address these Dragon Blood problems. Basically, maybe talking it a bit earlier, but we can cover them later. The Dragon Blood vulnerabilities were related basically with two main problems. Two of the vulnerabilities were related with the downgrade attack. So we will see later that if we are trying to connect to the AP using WPA3, an attacker can do something to force your station to go down to WPA3 preset key, and then start attacking you and capturing information, and later on do a brute force attack or other kind of attacks. This is related with two of the vulnerabilities, downgrade from WPA3 to WPA2, and the other vulnerabilities were related to the the capability of doing a deny of service attack. This deny of service attack is based on if you don't take care, the cryptographic calculations are expensive, so they will be done in the CPU of your laptop or your smartphone and in the AP as well. And if we send a lot of cryptographic transactions to the CPU, we can overload the CPU. So if the queues that are sending these messages to the CPU of the AP are not properly handled or are not are in the highest priority, you can probably overload the CPU, and at the end what is happening is that the AP will not be able to keep the beacons on the media, on the radio, and you will see like a deny of service attack. So this is the Dragon Blood recommendation that already been fixed. So even we in Ali, we didn't suffer them. And in any case, they are patches. I think all vendors already have patched them. So WPA3 is as secure as any commercial grade cryptography can be. So now let's move some basic about cryptology or cryptography. I know that most of you will know that, but as we are talking later on about something about related to this, I have to be sure that we all know this basic, which is in terms of encryption and authenticity of the information that is linked with integrity, we will see later. In terms of encryption, there are two worlds, let's say. So there are two different mechanisms to do encryption, which is symmetric key cryptography and public key cryptography. With symmetric key cryptography is quite simple, let's say, in the terms. So it is A trying to send a message to B. So they all use the same sharded secret, which is the key. So this sharded secret is well known for all the people that is willing to communicate with each other. So we do, in this case, a cipher by block, with this AES, the Advanced Encryption Standard, and then I generate sequence of bits coming from this message. This sequence of bits is sent to the destination, and the destination will be able to decrypt this information and recover the original message. The main drawbacks here is that the key management. So you have two guys sharing information. There's no problem because I can send you my private key by postal address with a USB, or I can send it to you while we are having a beer in the bar. So I give you my USB key that is protected, and then you have my secret, or we all share the same secret. But if the number of people scales up, like it is in the real world, it is a nightmare to deal with the key management. So it's impossible, and sometimes we have to forgot the key because it has been compromised. I have to renew the key and spread again the key is killing. So it's very problematic this point. What is the advantages? The advantages is that it consumes less resources than public key cryptography, and has a smaller keys to provide a very good level of security. So today, yes, for instance, being again commercial cryptography is quite secure today. And if you take care about the initialization vectors to be really random, it's very difficult to that someone can extract your key. Again, I'm saying you that if with commercial cryptography, if some government may have a quantum computer with 2,000 qubits, maybe, well, maybe not, they will for sure crack your message. But if you are using your message to exchange your last picture in the beach, I'm pretty sure that no government will be taking care of that. So moving now for the public key cryptography standards. In this case, each of the participants in the communication will have a set of keys. It's two keys, the private key and the public key. And the good thing here is that the public key can be share in the internet if you want. You can put it wherever you want. Is because this is the way it works. So when I want to send a message to B, for instance, I can either use his public key to encrypt the message because it's destined to him or her, and he or she will use his or her private key to decrypt. Or if I want to spread a message to some recipients, I can just encrypt with my private key. So all the destinations will use my public key to decode the message, and they will know that this message is issued by me because they know that my key is only my key. So it brings more added value here about authenticity. That's the reason I add here the authenticity. The drawbacks here, well, is much more time consuming, is much more CPU intense, especially now we are talking about IoT devices that are not horse powered, so they have a reduced CPUs and reduced RAM memory. So we are here in a worry, and smartphones are also impacted by, could be impacted as well with this. Which is the advantages? The advantages is the key management, as I told you, and one critical benefit here is the key agreement. We can agree on symmetric keys using public keys. As I told you, the problem here in symmetric keys is to exchange this secret key. So if somehow we can, using public key, agree in a shared secret, that's the best thing we can do, because then we can use the best of both worlds. We could use public key to generate this session key, and yes, use this session key, which is less consuming in terms of CPU and is very efficient in terms of security compared to the number of bits it has. So this is combining the two worlds is the best thing we can do, and in fact is what we do today and in our daily communications. So then we have to go to integrity. Integrity is other thing, which is as I told you, somehow we can guarantee that my message has not been modified in the travel to the destination. So integrity is achieved by hash or hashing functions, and these hash functions are one-way functions. That means that they have cryptography is basically mathematics. Is very impacted by the mathematics. So here we will talk sometimes about some mathematics concepts. So if we have a space of numbers, for instance, let's say the natural numbers, which is an infinite number, is an infinite volume of numbers. I want to compact them to, let's say, only numbers or the 200 first numbers. Okay, then I can create a function that will go from this space to this space. So this is the maps arbitrary size numbers to fixed size values. So this is the hash. For instance, in this diagram, you may see that I can put a message of 12 megabit or 1 gigabit or whatever bytes and apply the hash function, and I will get a 226 bits length message. But if I do the same with 4 bytes, I will get a 256 bits message again. So it doesn't matter how long the space here is, I will always get a short message of 220 and 56 bits in this space, because I'm using SHA 256 in this case. So the hash algorithm will go that way. So we'll go from the message to the hash, but it is impossible to go from the hash to the message. If you can do this, then the hash algorithm is hacked or is cracked, and you have to go to the next level of hashing algorithms. Remember that MD1 is considered to be crack. Sorry, MD1 for sure. MD5 is considered to be crack, and you should avoid the use of MD5 apart from very short time specific use of the hashing. Like for instance, in pairing with OSPF router with another OSPF router, you can MD5 apply MD5 to this exchange of LSPs, link state advertisements, or LSA, and use it because it's very short in time, but the use of this LSP. But if you're going to use it longer, you should not use MD5. So how strong is a hash algorithm? I'm taking here an example of Bitcoins. Probably Bitcoin is the best effort of creating a combined CPU process worldwide. So there's a lot of miners worldwide with their NVIDIA or MDA GPUs. They are doing this mining Bitcoins. At the end, mining Bitcoins, all these transactions require to do a hash, an SHA 256 hashing. And today, Bitcoin are doing 100,000 tera hashes per second. So just think about it, it's crazy the number. Okay, this is more or less, if you do the calculation, it is more or less a 2 to the power of 85 hashes per year. So all possible hashes are 2 to the power of 256. But according to the birthday paradox or the birthday problem, if you reach the half, you most likely will be starting to reuse destination hashes. So because obviously if you have infinite messages here in this space, and I'm going to compact them to a very limited number of messages here compared with infinitum, this is a very limited number compared to infinitum, and any number is ridiculously small. So at the end, if you use this hash algorithm, at the end, some of them will collide. Some of these two messages will create the same one, which is already forbidden for being a hash. So for hashing algorithms, has three properties. It's a one-way function. You can go back, so you cannot go back to the message. They compute always the same length message at the output, and there is no two different messages that compute exactly the same output message. If this one of these three conditions are broken, sorry, then the hash algorithm is considered to be cracked or hacked. So let's continue reaching this out with the birthday problem. When we reach the 2 to the power of 228, then we are compromising our hashing algorithm. So let's see what is happening if we continue using the Bitcoin, the same algorithm during the next 4 years. So this is 2 to the power of 85 plus another one plus another one plus another one, because it's 4 years. And then we have 2 to the power of 2 times 2 to the power of 85, which is 2 to the power of 87. Okay, it's increasing, but it seems not too crazy. Now let's try, for instance, 2 to the power of 16 here. 2 to the power of 16 is 65,000 years. So I don't know if Bitcoin will be still with us, but it's a long period of time. Okay, let's see what's happened. If we have 2 to the power of 16 and 2 to the power of 85, then we have 2 to the power of 100, 101. So it is ridiculously far away from 228, which is our limit because of the birthday paradox. So pretty sure in these 60,000, 65,000 years, pretty sure we will be reaching brute force attacks, or we will see quantum attacks earlier than the exhaust of the algorithm. So we should be comfortable with SHA, but again, as I mentioned, brute force or quantum computing will dramatically change this in the next years. So what can, okay, this is the theory about encryption and hashing. Which encryptions should be used or are most widely used in commercial encryption? Again, commercial grade encryption. The king is AES, which is the advanced encryption standard, is from the 80s, and it's still in good health as far as you do the things right, and as far as you use a good random number generator. If this random number generator that sometimes has been compromised, you will have, if you use a good random number generator, you are safe. There is some AES modes, we will see it later, with two of them, which are the ones used in WPA, WPA2 and WPA3, but there are others. There are other standards, for instance, in Russia or in China, or for military applications or for purpose-built applications. There are other cryptography standards that can be used for symmetric key cryptography, like Serpent or Salsa 20 or Chacha 20 or some others. And this and the coming information we are going to share with you is basically driven by these entities here. So it is then NIST from the US and NSA from the US. Then we have an agency, which is ANSSI from France and BSI from Germany. And then we have the Encrypt CSA, which is an effort for the European community or the European Union to try to be relevant in this space of the cryptology, sorry. And the NSIT, and this is linking with the quantum attacks, has already started to ask for researchers, mathematicians, all these guys to start thinking about the cryptography for the next 30 years or 50 years, because they are pretty sure that will be quantum computers being able to crack current mechanisms in cryptography. So if you go to NSA, for instance, and go to the recommendations for the 2030, they are not providing any recommendation at all, because they are pretty sure that all these mechanisms will be probably wiped out by quantum processing. Okay, let's go to public cryptography. I will not go into many details, but I think it's needed. In this case, the cryptography, the all cryptography systems are based on what is called trapdoor functions, or P, like this morning, P versus NP, which is the mathematical way of saying trapdoor mathematical functions. So trapdoors are functions that you can go, again, one way very easily, but it's very difficult to go the other way. You can do it if you know all the parameters. This is not the same as a hash function. In a hash function, it should be impossible to go back. So by definition, here, no. Here, if you know all the right parameters, you can go forward and you can go backwards. But if you go forward with all the parameters and you want to go backward and you are missing one of the parameters, then it is impossible for you, or will be very difficult, or you will need a quantum computer or something like this to crack the code. The most important and widely used public key cryptography standard by these ways is the RSI. RSI is from the 78, so just think about this, quite old. And the first time RSI was known was proposed by Diffie and Hellman in the 1976, and it's based basically in the complexity of factoring a large prime number. If you have a very large prime number, it is absolutely ridiculous the time you will spend trying to factor this number into his two components, prime components. This is an example. For instance, my private key in this case will be these two prime numbers, and I then multiply them, and I will get this public key. So this public key, I can share it with all of you, because if you take one computer and try to find out the two primes that are composing the number, will take very long time. It will take very long time for you, but remember this is an example. In the reality, this number, to be considered safe, will be about more than 200 digits. So it's crazy. So it's a very large number, and you will be safe if you keep that, because it's very difficult to crack this one. In the 80s, in the late 80s, 87, 88, I think, if I remember, they started a new paradigm, which is the elliptic curve cryptography, and it's based on elliptic curves. Elliptic curves are a polynomial function, x to the power of 3 plus x to the power of 2 plus x plus the number at the end. And this is based on the complexity of the discrete algorithm. So if you want to compute back, you need to extract the algorithm for this sequence that we are seeing here, and is computerally talking is very expensive. So here, for instance, this is one of these functions. This is the elliptic curve, and the way it works is that we start, for instance, with point A, and then draw a line, and we see point B, and we get this point here. And from this point here, we rotate to the other part of the x-axis. You see this is symmetric from the x-axis, and then go here. I reach this one, and then I draw a picture, a line there, and then I get this point, and then I flip, and then draw another line, get this point, I flip. So I do, for instance, 102,000 or 3,000 flips, or whatever number of flips, of cycles of calculating this way, and at the end I get the starting point A and the ending point E. So this is my public key. My public key is A and E, and I can give it to you, because it is, for you, is almost impossible knowing these two numbers how to go from A to E or from E to A, because you don't know all the calculations that I have done to reach it. And for me, my private key is exactly this number of cycles that I did. So it is impossible for a hacker to break this thing. This is equivalent. Sometimes in cryptography, you see something, some quantity mod some other quantity, some number. It is a clock calculation. In a clock calculation, which is more or less like this one, in a clock calculation, you may find it's very weird, because, for instance, this one, which is 12, mod 12, I have split it the cycle in 12. The 0, which is here, is exactly the same number as 12. So if I give you a 0, this last result, and I don't give you the number of cycles, you simply cannot extract the original number. So because you don't know how to do it. And this is exactly more or less the concept here. I don't want to go into the details, but just keep that this is a clock rotating calculation that allows this information. Why ECC? Why elliptic curve cryptography? Well, it is, remember I told you about the length of the keys and the computation resources. So with the larger the keys, the more resources for calculation. And if we compare RSI with ECC, there is a dramatic improvement in ECC, because to keep the same level of security in RSI, we need 3072 bit length keys, while we only need 384 bits in the key for electric curve. So just think about it, because in our world, we have smartphones, we have IoT devices, all these things. If you have to compute a lot of things, the easier for you, the better. And at the same level, keeping the same level of security, which is important, okay? Probably you are considering your laptop. Okay, your laptop is only doing one connection with the AP, but just imagine an AP. An AP with 200 connections, for instance, has to do calculations very frequently, and it's 200 calculations that are going to be done by CPU. So take care of that. Okay, now we have a review, which is the status of the recommendations. We have some overview about cryptology, and now let's go to see which are really the WPA3 benefits here. So there are more benefits if we combine one AX and AC versus WPA2 PA3, but this is, I think, the more relevant. So the first one, and is probably the key one, is how we do the key agreement in WPA2 personal with WPA3 personal. So here we use pre-shared key, and here we use a new paradigm, which is Dragonfly. That's the reason the report about the Dragonfly vulnerabilities was called Dragon Blood. So that's the reason. So Dragonfly is used here, which is SAE, simultaneous authentication of equals, and is using cryptography, elliptic cryptography standards. So we will see later why, in detail, why it is better to do this way than this way. And in WPA3 Enterprise, in order to do the agreement of the keys, the new thing is that we have extended the keys for the existing algorithms. For instance, RSA can now go up to 3072 keys, bit keys, and Diffie-Hellman RSA is 3072 length in bits. But now we can use elliptic curve Diffie-Hellman with 394 bits, which is a new thing here. Moving to encryption, well, here nothing changed, more or less, because AES is considered still a very safe algorithm in commercial grade. Remember, it doesn't matter that maybe some government or some very important organization may have the means to crack it or to extract the information, but for our world, for our commercial world, is more than enough today. Nevertheless, in WPA3 Enterprise, we add an improvement to AES, which is AES 256, which is Suite B. Which is Suite B, you will see here. Suite B is a set of cryptology standards that are recommended by the NSA, for the US NSA. And it is related with encryption using AES 256. It is related with the hashing algorithms. They are moving away from SHA2 and moving to SHA3, so in this case 384. And signature, how to sign documents with elliptic curve 384. Key establishment, Diffie-Hellman elliptic curve 385, and this is considered to be a secure level of 192 bits. So that's the reason we are adding this Suite B. Is the one of the top level standards today for cryptography according to the NSA terms. So the top level security level here for commercial grade. And this suite B has been evolving with the years. So most likely, if you go to look for the look at the suite B in 2 years, or 3 years, or 5 years, due to the fact that quantum computing is entering into this space, most likely these encryptions have changed, may have changed. So let's keep an eye on it on this. Then we have an integrity, which is CBC MAC, quite old, and you can see some, you can extract some information from the time it takes to compute. So, well, it's considered to be not so strong. And here we use again these cryptographic elements, Galois contact block mode with 128 or 128, which is this is the new standard here in WPA3. With the session key size, that the session key is the session that we are finally going to use. Session key is a symmetric key, remember. So it's not a public key. We use public key to generate this session key, but this session key is symmetric key encryption, and you can see an increment in the number of bits, a little bit safer. And protected management frames. This is very important for our space in wireless LAN, because in WPA3 it was optional. So all the information we exchange, these management frames were in clear. So was very easy to get information. Probably not the most relevant information, but I'm getting information. If I capture enough information, I can do something with it. In the late 2018, it changed, and now it seems that now is required, but most implementation are still stick to the optional requirement from WPA2. And WPA3, even in personal or in enterprise, it is mandatory. So you have to encrypt and protect your management frames. We will see later. There's one case here in WPA3 personal where it is not mandatory, which is optional, is when we try to use both WPA2 personal and WPA3 personal at the same time in the same SSID, which is called the transient mode. But that should be avoided, but it is there in this standard. So why is so different to use WPA3 personal and WPA2 personal? Okay, let's look at how the keys are generated. In WPA2 personal, we have our preset key, the same here, the preset key that is the one we use when we create this SSID, and we say 1, 2, 3, 4, 5, 8, 9, 0. So this is the preset key. And then in WPA3, there is a hash algorithm that computes the pairwise master key. Then there is a four-way handshake where the attackers will capture information or may capture information, and then we have the pairwise transient key, and then the session keys, which are we are going to use. In WPA3, the scheme is more or less the same. The difference is that here we are using another algorithm, which is Diffie-Hellman in using elliptic curves. Then we use the same preset key, could be here, and this is this new algorithm. SAE is symmetric authentication between equals, and then we generate again the PN key, full-way handshake, PT key, and the session key. So what is so different here? Okay, remember the hashing algorithms. Hashing algorithms will always generate the same message from the same source. So here, this PM key will be always the same. Will be always the same as far as you don't change the PS key. So if you have your PS key 3 months, 6 months, 1 year, you have these keys here for 1 month, 6 months, or 1 year, or whatever time. And then in this four-way handshake, there is some clues which are known in initiation vectors or nuances and MICs. If you capture enough information here, then you can go offline and try to do a dictionary attack to your Wi-Fi key and find out this pre-shared key. What happens in WPA3 personal? In WPA3 personal, every time we try to generate a new session key, this PN key will be different because we are using a complete different animal in the cryptography world. So this animal will generate a complete different bit list here. So it is impossible for any attacker to find out what is going on here, because it will not have enough time to find out information. Again, you can capture IVs and MICs, but as in the next 30 minutes or in the next hour, I will change my session key probably. You will not have time to decode my pre-shared key, or will be more difficult for you. So now moving to WPA3 and on the Vista and Stellar, how can we configure WPA3? Okay, if we want to generate an SSID with a pre-shared key, then we can name it WPA3 or whatever you want to call it, SSID. And then in the encryption type is you can see that is a list, and this list has two new members. The first one is WPA3 SAE AES, and this is if for only using the new WPA3. Okay, so if you are going to use WPA3, let me check what is happening here. Okay, if you want to use only WPA3, this is the one you have to use. In fact, this is the one you should use, because the other one is the transition mode. The transition mode allows for a single SSID to both simultaneously WPA3 and WPA2. So legacy devices that are not able to support or will not support WPA3 can connect to the same SSID as the WPA3 most modern devices. But you are then exposed to some downgrade attacks. This downgrade will can make you as an station to go back from WPA3 to WPA, and then we can expose your key. So remember that this is important, and if you can do it, please go directly to SAE. If you cannot, then go here and then try to combine this with the device-specific pre-shared key, which is another feature that we have, that in the same SSID, we can have different pre-shared keys. So for instance, I don't know, the laptops will have one pre-shared key and the smartphones will have another pre-shared key. This is not a security improvement or much security improvement, but at the end, well, if you expose one key, probably your other key is not exposed, or so this, if the hacker has enough time, will break both. Okay, but try to do something like this, try to complex the life of the hacker trying to enter in your system. Again, moving a little bit down in the page where you configure the SSID and go to the protect management frame, is required. Is required if you use WPA3 SAE. Obviously, if we in the same SSID are using the transient mode, then we cannot force to protect the management frames, because probably the legacy device will not be able to do it. So here, if you change here to this option, to pre-shared key AES, you will see that this changes as well and is set to optional. This is the only way that you can see related WPA3 with optional protected management frame, only when working in transient mode. With WPA3 Enterprise, that is with the 1x radius and so on. By the way, WPA2 Enterprise is considered to be safe, because at the end, you are not compromising any key exchange. Obviously, in WPA3, we are improving the key agreement and the key exchange as well, but because we increase the length, remember, we increase the length of the RSA ciphers and so on. We add now the elliptic curve cryptography. So there is an advance, but today is considered to be safe, a WPA2 Enterprise. But in any case, if you want to go to the top level security standards today available today, then you have to go to WPA3 AES, or even more, you have to use the Suite B, which is the NSA Suite B. This WPA3 AES 256 is the Suite B. Yeah, then we used to use the top level commercial grade cryptography standards up to date. So now we finish this part. Now let's finish with two more points that are related with security, but not with the encryption or integrity and these kind of things. Is what about the management plane? About okay, we know that all our APs and OmniVista has an Ali CA issued certificate, so both can talk because they both exchange the certificate and they okay agree. You have one IP from my CA. I am OV. You know that I am certified by the same CA. Everything is fine. Let's talk together. But we can move into strong security requirements in public organization, military, police, government, where they can simply not trust on our CA, which sounds perfectly logical, and they are willing to leverage their own PKI. So then we will need to issue a certificate for the OmniVista, and we will be able to issue a certificate for the APs. And the APs will try to connect to the OmniVista. OmniVista with his new certificate coming from the PKI will gather all the information from the APs still using the legacy or the Ali CA certificate, will capture the information and will send upon the administration request, will send this information to the registration agency, to the RI, which is one of the parts of the PKI of the customer. And then using SCEP, we will then generate the certificates and will be delivered to the OmniVista. And then OmniVista will install these certificates in the APs. So it's an automatic way of doing the thing, but we really recommend once it is delivered, which is scheduled by November timeframe, we recommend to do this enrollment in a secure network. If you can isolate or you can be close to the OV and close to the PKI when you are going to enroll the AP is better because you are pretty sure that no one is in the middle doing something strange. Remember, we're now entering into the paranoia security, okay? This is another word. And the last thing I would like to share with you is the AP will support W1X as a client as well. So if you find you are facing the need of authenticating the AP once they are connecting to the network, to the switches, to the Omni switch or the vendors, and you want to be sure that this AP has the credentials you need to grant access to the network. Now, again, in the November timeframe, the AP will be 1X supplicant as well. And that is all from my side. I really like to thank you all for being very active today, attending my session. And Diane, if you
Sure.
can help me with the...
Your presentation was so thorough, there are no questions on the question panel.
Okay, perfect. That's great.
I know I got a lot. WPA3 is more math in this than I ever. So does anyone in the panel have a question, or I'm happy to unmute your line if you'd like to speak directly to Jorge also. If you want to raise your hand. I don't see any of that. Hopefully everyone had a chance to download the presentation from the handout section. Again, if you didn't, you'll get an email tomorrow that will have a recording embedded with it, and then also just reply to the email and I'm happy to send you. I can also send it to you in PPT format too. I know we load it as PDF. So, and thank you, Jorge, very much. Great job.
My pleasure. My pleasure. I'd really like to thank you, the audience, for being here with us. Thank you very much, guys.
Yes, thank you.
At any time, just reach us, contact us, and we will be able to help you with these questions or any other questions you may face.
For certain, yeah. Okay, thank you. Bye.
Thank you. Bye. Take care.